As always, you can choose to write these down. You can choose to print them off from Schoology. You can choose to take a picture if you want. You can choose to video this entire thing. Jimmy cracked corn. I don't care. You just need to know it.
What's Jimmy cracked corn?
It's a song.
Yeah.
No.
No.
Is it popcorn?
The cracking of the corn refers to the grinding of the corn to make cornmeal. Not crack, no. Cracking is like the breaking of the kernel of corn. This is not on a handout. This is not on a handout, but it's entirely up to you how you want to record this. I will tell you, however, that basically what I'm doing is I am summarizing what's on this handout here. So you basically have all this information here. If you choose to just sort of go through this and highlight the important things, that's also good. Entirely up to you how you want to do that. Okay? Page 8.1. So, friction is simply a force that resists motion.
What is it?
Friction is a force that resists motion.
We taking our own notes? What is this for?
Lucas, I'm going to pause for 30 seconds.
You're summarizing.
So, when you've got friction, you must have objects that are in contact with each other. There has to be contact. Is air resistance a type of friction? Yes, things are in contact with the air as it slides through. Air is actually a fluid. Think about if you're walking through. Why is Alex on his phone after I gave like about 8 minutes at the start?
You should kill him.
When you walk through a swimming pool, do you feel resistance against the water? Yeah, you do. In fact, people use that as it's a good rehab exercise, right? It's good exercise. It's low impact on your joints. Same thing when you're walking through the air. You just don't realize it because that's how we live, right? But there must be contact. Okay. So, some causes of friction. Now, friction is actually one of those things that's not really well understood. It's everywhere. People know what it is, friction, right? But to actually describe it scientifically is a little bit of a challenge. So, they actually believe that an object deforms a surface and vice versa. In other words, they actually believe that if I draw a picture here,
When you say they believe,
well, scientists.
You don't believe this?
It's believed, like scientists,
You
right?
believe.
Yeah, I think so.
Why say they when
Well,
it is?
it's believed. It's believed to be. Good point. So they're actually saying that the book or whatever's sitting on the tabletop actually creates a little tiny hollow, deforms the surface, right? And that a plowing force is required, an uphill, up the ramp kind of force is required to move the object over this deformation. That's one of the theories. Another theory is that irregularities interlock and offer resistance to movement. In other words, you've got this table that's considered to be smooth, but it's really kind of like that, right? And then you've got, so it's rough, right? And they sort of run into each other, and sometimes those little irregularities might break off. Like if you're down in the wood shop and you're sanding a piece of wood, the idea behind sandpaper is to do what? Rub off some of that rough wood. Rub off some of that sandpaper. That's the whole idea. There's a school of thought that actually, if you make the surfaces so smooth that you actually increase friction. Any ideas on why that might be? They're so microscopically smooth, right, that they're actually, if there's more contact, that's one thing, and you also create a bit of a vacuum as well, which is hard to sort of, kind of like when you put your finger on top of a straw, that kind of thing, that kind of vacuum, right? It's kind of, you hear that little pop when you pull your finger off, that kind of thing. So friction, in other words, what I'm getting at is friction isn't really well understood. They can't really say, well, it's because of this. It's still being debated. Okay, a couple of points here about starting friction and sliding friction. Starting friction simply means how much friction at the... Exactly, how much friction at the start. It's the maximum frictional force between stationary objects. There's always more friction at the start. I don't think they know why.
This is not moving.
Well, it probably has something to do with inertia. Sliding friction is the frictional force between objects that are sliding with respect to each other. So in other words, like if you push a chair across the table, or a chair across the floor, no, not across the table.
That was really bad.
Okay. There is another one that I don't want you to write down. Rolling friction. Rolling friction is, as Kurt points out, a little misunderstood. I've been told that rolling friction is actually an example of starting friction, because as the wheel rotates, right, it's that little bit of wheel that's in contact with the ground that's, right, and then there's another bit of the wheel. So it's actually starting friction multiple times, kind of thing. So rolling friction is kind of complicated. We will, for all intents and purposes, ignore it.
Why themselves, they just ignore it.
Because people ask about it, right? Well, what's the deal with rolling friction?
You've never told me.
On.
Okay, some properties or characteristics of friction. Nate, I've begun. The key here is the word parallel. Friction is always parallel to the surfaces that are in contact, and it's always opposite to the motion. What if there is no motion? It'd be opposite the motion if there was no friction, right? Like, so for example, if I push against there's a big counter here, obviously it's not moving, there is some friction holding it in place, it's bolted to the ground, right? But the friction is still opposite the force, right? So it's parallel, and it's opposite the motion. Always, always, always opposite the motion.
Then also when you push on, is that a counter for it?
Friction depends on the nature. Friction depends on the nature of the materials in contact and the smoothness of the surfaces. So like I was talking about there, if there's ice, if I'm wearing a Teflon slider, if there's like gravel on the floor, whatever, the friction depends on how smooth they are. Here's a key one here. Sliding friction is less than or equal to starting friction. So starting friction is starting friction is always more, greater. Sometimes equal. Be careful. Sometimes equal. And then I'm going to talk about number 4 here. All right. Point number 4. Friction is practically independent of the area of contact. Most people think the greater amount of contact, the greater amount of friction. Not true. Not true. Allow me to demonstrate. It doesn't depend on the surface, right? Allow me to show you here. Okay? I've got a book, right? And I don't really have a table up front here, so I'm going to have to go back here. But if you imagine this book sliding across the table, there's a certain amount of friction, right? Does it matter whether I have it like that, or whether I have it on its back or its spine, like so?
Yeah, I think those small sooner.
Okay? Friction is the same. Obviously, it won't stay up like that, right? As long as the face of the book and the spine of the book are made out of the same material, the friction is the same, because the friction force depends on the weight force, and the book doesn't weigh anymore because it's sitting flat or it's sitting on its spine like that. Okay?
So pushing it.
Amount of contact area does not have anything to do. It's practically
A
independent.
different material.
Okay? So, well, obviously, right? What you're thinking about is pressure. Pressure.
Oh gosh.
Pressure is dependent upon area.
I think.
Okay? So it's a common misconception. You think about people think like the narrow tires of like racing bikes and stuff like that, more friction. It's a little more complicated than that. Okay, and the last one, starting or sliding friction is directly proportional to the force pressing the two surfaces together, which is generally the weight force. That's what it is. It's how much weight. Do you remember when you did the lab? And you had the wood block like this, and you kept adding weights on top? And it slowed down, right? You are in fact increasing the weight force, which in turn increases the friction. Okay, so what this all boils down to is this. This is referred to as the coefficient of sliding friction. And it is the ratio of the force of sliding friction to the normal force. It's the force of friction over the normal force. The coefficient of sliding friction. This funny looking symbol right here. It's like a U. It's the Greek letter mu. Okay? It's like a U. It's got a tail on the front. So you sort of draw a line like that and then you make a U.
What's a rash instead of reach? Hey, don't be way better than last class.
The Greek letter mu. Now, I don't know what Greek high school physics students use. I've always wanted to ask them, but I think it would be creepy if some weird guy came up to a Greek person on the street and said, "What do you use for the coefficient of friction in your high school class?" So I didn't do it when I was there.
Maybe they use a Canadian name.
Maybe. I don't know, but then the F's would be in Greek as well, right? And this is the Greek M, so what do they use for M for mass?
What do they use? What do they use?
I have Googled it. I can't find an answer.
Didn't you Google it?
Yeah, I really wanted to ask people, but my wife says, you can't do that.
Yahoo Answers.
I think of
I
paradox or
have
what?
some dumb questions, but I'm like, what country?
Yeah?
They're not going to see everything. Where are you going?
It's a good attitude to have, man.
So Google the answer.
Okay.
I was not done.
Oh. Okay, you should have a double-sided sheet with examples on there so that you've got them, so you don't have to write them out. Let's jump right in here. As always, the degree of difficulty will increase as we go. So, a box with a mass of 175 kilograms pulled along a level floor with a constant velocity. You should see bells and whistles. I guess you wouldn't see whistles. You would hear bells and whistles. You would see flashing lights. Constant velocity is key. If the coefficient of friction between the box and the floor is 0.34, what horizontal force is exerted in pulling the box? Let's, as always, begin by drawing a diagram.
Or back those force though.
Oh, yeah. Yeah. Okay. Now, what does this have to do with gravity? Because what produces friction? Gravity. Okay. So we've got 175 kilos. Okay. There is friction. We always assume things move from left to right just because we live in a left to right society. What does the constant velocity mean? It means the forces are balanced. Nate, the forces are balanced. So the friction force is equal to the applied force. The friction force is equal to the applied force. Okay, so we are solving for FA. The way to get FA is to find the FF. Weight force down, normal force up, right? Okay, what is your spidey senses telling you is the first step?
I'm going to do it 175 and 0.5.
Let's find the weight force, the force of gravity. 175 times 9.8, or 1,715 newtons.
$17.15.
1715.
So that would equal normal force?
That, exactly. Because, is this thing accelerating vertically up and down? No, it's just sitting there. So this means that the normal force is 1,715. Right?
Is it equal?
Okay, guys, focus on this, okay? Seriously. Okay, now that I've got that, our new formula is mu equals FF over Fn. Our mu value is 0.34. Notice how I'm lining up my equal signs. Whoops. Friction force is what we don't know.
You better not have to erase it, because this is all, how do you know?
My normal force is what's going in there. And how am I going to solve this?
1,700.
Yep, 1,715.
Whoa.
It's not an M, it's a mu. Oh, you mean this M up here?
Go down there.
This one.
See, that's a U.
That's a U. That's
Oh my God.
that's this, Nate. This thing here.
Friction translator.
So that's the coefficient.
That's the coefficient. Is that funny looking Greek sign?
That's okay.
Yep.
Okay. Shut up, Nate.
So it's 583.1. Dane, pay attention, man. Seriously.
Did Dane get one?
I have a question.
Is it 0.1 U?
The coefficient of friction is equal to.
Is that an N?
Yeah.
Yeah.
The coefficient of friction is the mu, yes.
Why don't we just write 0.34 then?
I did.
Oh,
I wrote the formula.
Plug
And
the
then,
numbers
yeah.
in, yeah.
Yeah. No.
583.
Okay, so the force of friction is 583.1, which means that the applied force is also that.
So basically, it's like figuring out normal equation, but you gotta do a bunch of stuff.
Well, all I've really done here is brought in this idea here, right? It's just one more level of complexity to those questions we did last unit, really. That's all it really is.
I like these zeros together.
Okay?
Now the hard part's gonna be doing them without your help.
I know. Well, I'm going to be there to guide you for a while. It's like riding a bike with training wheels.
Never done that. But I just.
You know how I learned how to ride a bike? You know, like my grandpa took my bike. Took the training wheel. How did I get one? How did I get one? I have a question. How? I didn't even do it.
You know how I learned how to ride a bike? That was what you said.
We use our doggone bikes.
Don't worry, Lucas, you're not going to win.
Yeah. He just threw his bike, put my bike on the ground, and he just got his car and drove away.
Said, tough luck, go ride a bike.
I was like 3 miles out of Sip, and he like just said, yeah, drive your bike home.
Good.
I didn't know how.
It's tough, man. Tough life. Okay, example number 2. Now, I want to point out that I realized I went right to example 3 before, and it was way too much of a jump. So I put in example number 2. I don't want to give you too many examples because then it's sort of overload kind of thing, but I think I'm trying to hit that sweet spot in between easy and hard.
He did it.
A box with a mass of 100 kilograms is accelerated by a force of 200 newtons across a level floor. Key word here. Level floor is key as well because you can't do ramps quite yet, but accelerated. What does accelerated mean? What's that code for?
Spelled incorrect.
Forces are not balanced. Right? F net not equal to 0. It's accelerated by a force of 200 newtons across the level floor. If the coefficient of friction between the box and the floor is 0.2, what is the overall acceleration of the box? Yeah, I saw it. Okay. What do you think the first step is? What should I do?
On the weight force.
Yep. Come on in. Okay, so what's different here? The applied force is much greater. Much greater. Are the vertical forces balanced? Yes. To find overall acceleration, what's the step right before that? Right? Find the net force. How does this one compare with the last example? What have I added?
You're looking for acceleration.
Exactly. I'm only adding which step? Right here, right? I'm adding another step in here. Because the friction force and the applied force are not the same. So, as Helena, actually, I think it was her said, find the weight force first. $980 newtons. It's nice when they're easy like that, right? Keeping in mind the net force is going to be applied force plus friction force. Do I know the applied force already?
No. Oh.
Right?
It's not in
It's not on yours?
It's not in there.
No, we're not getting it.
Oh, I apologize. Okay.
That thing deserves fix. Did you hear that obnoxious sound that I do all the time?
No, I didn't actually. I was engaged in a conversation over here.
Big, this is a big contest.
You're probably right. I'm trying to make a point, Nate.
There's no point to get.
Okay, so I do apologize. I'll have to fix that. So after I found the weight force, what did I do before? I use our new friend to find friction. Mu is FF over Fn. This, by the way, equals the normal force, right? Is it always going to equal the normal force? For you, yes. For you, yes. It is only true when it's on a level surface. Okay, so our mu value is 0.2.
The music keeps looking like an
It's a U. Actually, it's the Greek M.
So as soon as we see something that says if the coefficient of friction is on between the box and the floor, then we know we have to use that mu.
Yep, absolutely.
Is it always going to give it to us?
Unless the question asks what's the coefficient of friction.
How are you going to find it?
Then you'll have to know something else, right? Like you'll have to know one of these other things that I'm finding here and work backwards kind of thing. Yeah. Okay, so we've got a friction force of 196. Before, in the last question, we just said, okay, yeah, that was the applied force. But now, I'm given the applied force, and I'm asking you to find the acceleration, or in other words, the net force. So what is our net force? Well, that's going to be the applied force plus the friction, keeping in mind that the friction force is always negative, and so it works out to be a paltry 4 newtons.
What's a paltry?
Small.
Kind of like mu.
That one was worth it. That one was worth it. I'll take that. I'll take that immediately.
I had to give it to you, but yeah,
Still very
Oh, but yeah.
it was worth it. I almost said it myself. Actually, I was gonna make a joke about chickens.
Oh, wait for my chicken legs too, are we today?
Poultry. I'll give myself one there.
Oh.
So I got way off track.
That was big.
I give myself one. Did I deserve it?
Yeah,
I think I do, yeah. I deserve that
You
one.
did.
I did. Hey, I'll take it. Okay. We're now at the net force. What am I trying to find? Acceleration. Next step. F net is equal to MA, right?
Yeah.
4 is equal to, isn't it like 100 kilos?
Like, how are we supposed to know that though?
It doesn't,
100 kilos.
doesn't like there,
Where?
like fourth letter.
Okay, gotcha. Yeah, I saw.
I have to point something out. If I had showed you this problem back in, say, about the second week of October, what would have been your thoughts?
What the hell?
Oh my God, that is way too hard. I have no idea what's going on. And now, no problem, right? Have you learned anything since the 1st of October? I think you have. No, but you can solve that. No one's freaking out on me. Like, back then, I gave you something like this, and all I heard was, like, complaints. You've come a long ways. Having said that, here's the next level.
Here we go.
I heard someone say over here, oh, it's one of those horizontal ones. What do you mean, Brennan? It's one of those ones where you got to find the...
FM, FH.
Yes, exactly, Nate. You know what I'm going to do, Nate?
What are you going to do?
Take one off.
I'm just going to let it go, because I'm tired of walking over there. They're right.
Well, it's good difference in me is seeing how we get a whole piece in one question.
Yeah, it's not too bad.
Taking a lot.
Now, I hate to do this to you, but I'm going to add another level in here. I want you to draw in this one right here, and I'm going to label it FV.
What's that?
Well, the H stood for horizontal. The V stands for vertical. Now, what does the vertical component do? It kind of lifts it up, right? When someone's trying to push something heavy, what's one way to sort of make it easier?
Lift it up and
Lift it a bit. How come?
It gets it off it.
It gets it off the ground and it reduces friction. Here's the math behind that. Okay, so I made it nice and straightforward here. What is the horizontal component? What's the normal force? And what is the coefficient of sliding friction? So here, Lucas is an example where you're not given the coefficient and you have to find it. Okay, step 1, it told you find the horizontal. It's always FA cos theta. So 260 times the cosine of 30 degrees.
What is it? Oh, no, no, no.
225.2. Now it doesn't ask for the weight force. Do you think we need to? Oh no, I have it. I have it here, right? Yeah, I have it here. I calculated it and then I realized I already got it. Okay. What is the normal force? Now, traditionally, I've just done this and sort of, gone through it real quick and said, yeah, those two are always equal. Is that true this time?
No.
Why not? Because what I'm really saying when those two are equal, what I'm really saying is that the net force is 0, and the things that make those up are this, and so therefore they have to be equal to each other. But now I've got this little guy causing trouble. Which, is he reducing the normal force or is he adding to the normal force? Reducing. Okay? The weight force is 450. Normally, the normal force would also be 450, right? But you're applying a little bit of upwards force, in a sense, sort of helping out the normal force. So the sum of these two is equal to this, right? Technically, it looks like this. Well, let's first of all find the vertical component. If the horizontal is FA cos theta, then the vertical component is going to be FA sine theta. New formula.
Why is it tan though?
Because tan is opposite over adjacent, and we know the hypotenuse here. So hypotenuse is sine over hypotenuse. So 260 sine.
What's later memorable again?
Right around.
Next on holidays causes accumulated.
Coca-Cola.
Keeping it on the aggravates or something?
Something like that, yeah.
Ah.
Thanks for sharing.
Agitate. You know what? It works. Just rate off.
130. So, mathematically it looks like this. I'm going to show you the mathematical way, and then I'll sort of explain it common sense kind of way. The net vertical force is the weight force plus the normal force plus the vertical component. Those three are what are existing vertically, right? And the net vertical force is a big fat 0 because it's not going up or down. The weight force, 450.8. The normal force we solve for, and the vertical component. Now, I made a mistake. What was that small little mistake that I just made? No idea? That's got to be negative. Right? It's down. Okay? Does it matter here? You betcha it does. The vertical component, plus 130. Okay, so now I'm going to take the plus 130. It's going to go to the other side. I'm going to take the 450.8 to the other side.
Does it become negative 130?
Yeah, and I'm going to be left with normal force on the right, and I'm going to have the plus 450.8, and I'm going to have minus 130 there. And you can see that the normal force is simply this weight force minus that vertical component. I'm helping it out. I'm really close to done. The normal force is reduced. By how much? By whatever the vertical component is. As you lift it up, you reduce that weight force, it reduces the friction. Makes it easier to move. What would happen, Nate, if I were to increase the angle here, say to 40 or 50 degrees? What would happen to the friction? Would it go down or would it go up? Or stay the same? You go down, right? As you increase this angle, more and more of your force is directed upward, and it makes it easier to move. However, by increasing that angle, you don't have quite as much sideways push, right? Okay, so now my normal force is 320. Last step is to do what? What's the actual question say? What is the coefficient of sliding friction? Mu is FF over Fn. Friction force? Oh. Do I have a FF anywhere written down here? I do not. Let's go back. There's the friction force right there. What's it equal to? It's equal to FH if and only if?
It's not
Constant
colored.
speed.
Constant speed. I didn't say it when I read it because I didn't read the question, but there it is there. Because it's moving at a constant speed, what does that mean? In this case, the FH is equal to the FF. And now I can put my 225 in there. And my normal force is this number right here. And you get a mu value of 0.7. I got two questions for you. You're right, mathematically we're done. What's the units for mu?
KG. Mutant.
Yeah, mutants.
Mutant.
What's the formula or the unit for mu?
You tell me.
I'm asking you. I know.
I hope.
Well, what's the unit for the thing on top here? Friction force is measured in?
Divided by newtons.
Newtons divided by newtons. Can't you cancel units?
So there's no unit.
There are no units for mu.
Trick
It
question.
was a trick question. I'm a tricky guy.
You already knew the answer, why don't you ask?
Because that's my way of teaching you.
Yeah.
There are no units for mu. I repeat, there are no units for mu. It is force over force. It is a ratio of forces. Now, some of you may have noticed, this is 0.7. That's a small number. The previous one, what was the coefficient of friction? 0.2. That's a small number. The previous one, the coefficient of friction is 0.34. Again, less than 1.
So if you have a big number, you're doing something wrong?
Generally speaking, frictional coefficients are less than 1. There is a list of them in this handout that I gave you. You flip it inside there, bottom left-hand corner, there are a whole bunch of coefficients. Rubber tire on dry road is 0.7. There's a lot of friction there. Teflon on Teflon is 0.04. If you get a frictional coefficient that's bigger than 1, there's a good chance what?
You did it wrong.
You've done something wrong.
Glass on.
I'm not guaranteeing it, saying that there's a good chance.
So it is usually under 1, but
Generally under 1. Generally.
Huh.
Okay? I think that's it. Any questions? A lot of questions, right?
Can we go to Frank's break?
I'm gonna mind blowing right now.
Yeah? Mind blown a little bit? Finding it a little rough?
Eye tracker, brain.
I think that's what I'm doing.